Hello everyone, my name is Chapu and come from the University of Aizu. And today I'd like to have a presentation about the chaotic method-based symbolic regression in genetic programming. So here are the contents. At first, I'd like to show you guys some background knowledges. So at first, the genetic programming is one of the evolutionary algorithms but it's quite different with another three kinds of evolutionary algorithm. For the genetic programming, you are not only need to optimize the value of the final result, but also need to optimize the construct of the results. So that means the purpose for the genetic programming is going to find a module is going to generate a module that are able to automatically solve the problem. And the next is here is some feature for the genetic programming. The first is there are no limitation of the data sets for the solution. Second, does not make a distinction between the searching and solution spaces. So that means, for the genetic programming, we don't need to transfer the data. We don't have any encode or encode process anymore. Like, if you applying the genetic algorithm, you need to transfer the data to the binary number, then transfer the binary number return to the data, right? But we don't need that anymore for the genetic programming. And the third is the solution represented in very specific arithmetical manner. Okay, so that means the data generated, the construct generated by the genetic programming, they are linked with each other. Each node is linked with each other. So you cannot shift the node. You cannot randomly shift the node like another optimization algorithm because they got a fixed relationship with another nodes. So the data structure used for the genetic programming usually is based on the linked list, such as a tree, a stick, or a graph, or map, or graph, something like that. Okay, so next, the tree-based genetic programming means for this study, we will only focus on the tree-based genetic programming. And the tree-based genetic programming is also called the Causa scale genetic programming because it is invented by the Causa around 1992. Yeah, and I will not to introduce in detail about the tree-based genetic programming. I will only to introduce you guys how does a tree-based genetic programming to generate a new tree. Okay, so we have two kinds of nodes for the tree-based genetic programming. The first is the terminal nodes. The second is the operator nodes. And every time when we generate a new node, we will have a random search to decide it is a terminal node or it is a operator node. Then if it is a operator node, we will have a random research again to decide what kind of operator it should be. And each operator will have equally likely of a probability to be chosen. And here is a crossover phase for the tree-based genetic programming. You can see they just exchange their subtree and its mutation. And for the mutation of the, for the tree-based genetic programming, you need first, you just need to randomly pick nodes, then to generate a subtree, then use this generated subtree to replace the selected node. That is the mutation process for the GP, tree-based GP. And the next, I want to show you guys what is the symbolic regression. At first, let's say the definition of the symbolic regression. It is searches the space of mathematical expression to find the model that best fits a given dataset. So basically that means the output of the symbolic regression is a mathematical equation, and the input of the symbolic regression should be a sort of data set. Then the generated formula should are able to explain the fitted data. So that is the purpose for the symbolic regression, and maybe you consider that we can use the symbolic regression to help people, to inspire people to discover some new knowledges, such as like some new physical relationship or new mathematical rules, something like that. And the next is about the logistic mapping. So the logistic mapping is one of the chaos mapping, and in the left side, we can see there has some feature for the chaos mapping. The first is the sensitivity. That means the initial input data is sensitive for the chaos mapping. That means, for example, there has two input data, and although the difference between these two input data is very small, but the output, generated mapping gonna be totally different. The second is randomness. That means generated mapping looks very random. And the third is also the most important one. It's called ergodicity. Okay, so I will use the example to explain what is ergodicity. Let's say the right side, this figure, it is a figure for the logistic mapping. And if we set this R equal 4, this time we will call this equation achieved fully chaos statements. And once a chaos mapping is being the fully chaos statements, that means the generated number gonna traverse all of the certain space. For this module gonna be between the 0 to 1. So generated number gonna traverse all of the number between the 0 to 1, and all of this number will not be repeated. So that is the ergodicity. And a lot of researchers thought it can help us to improve the performance for the searching algorithm. And next is a motivation. So actually it is very simple and intuitional idea that as you know, for some specific data sets, it is very obviously that some operator is not suited for those kinds of data sets. So, but for the conventional generative programming, each operator has a equally likely probability to be chosen, right? So for sure, it's gonna it will not have a obtain very good performance if each operator has the same probability to be chosen. So my idea is we will have a pre-learning. Then the input of the pre-learning is the target data set. Then output of this pre-learning is several selected probability mapping. Then we can use the Rowlett algorithm to assign the each probability to each operator. So that means after our pre-learning, each operator will have a different probability to be chosen. And for the specific question. And here is a pseudocode for the simple pseudocode for the proposed method. So okay, let's focus on the line 3. As you can see, we have the pre-learning here, and after pre-learning, we will have some probability mapping. Then we will use the logistic algorithm to assign the probability mapping to specific operator, so that each operator will have their own probability to be chosen. Then we can start our conventional the formal generative programming. Then once we generated new nodes, this time we will have a random search to pick one of the selected probability mapping to generate the tree. Okay, so you can find that we have a pre-learning here, and this problem definitely it's a NP-hard optimization problem. So we can have a lot of implementation for this pre-learning. And for this study, so far we just implement 2 ways. The first is a the random search based pre-learning. Second is genetic algorithm based pre-learning. And the right side, the pseudocode is for the random search based pre-learning. And because of time limitation, I will not show you guys explain in detail to you guys today. If you're interested in, you can contact me later. Okay, so it is a follow chart for the random search pre-learning. Okay, so in the end, I'd like to show you guys some experiments results. The first, and we will have 3 stages for this experiment. The first is comparing the conventional generative programming and with a new method. Second is discussing the influence of the different random number generator. We used some chaos mapping as a random number generator, so we will do this computation between the different chaos mapping. The third is discussing the different pre-learning method and the limits total computation. As a side, we have 2 achievements of the pre-learning. The first is random search. The second is genetic algorithm. So we will to comparing these 2 algorithms. So I'd like to introduce the data sets I used for this experiment. It is called Yan hydrodynamics data set. It is to describe the relationship of to record some data for the Yan's hydrodynamics, and it is belong to the physical field, and there has 7 totally attributes. That means we will have 6. It is a 6-dimensional problem. We will have a 6 feature and 1 label, and totally we got 308 data. So here is a default parameter setting for the genetic programming of this experiment. The population size is 200, iteration is 100, inter-tree size 3, mutation rate is 0.6, and operator sets, we got the 9 operator for this experiment, and terminal set is from the x0 to x5, there has totally 6 different terminal sets. The selection method is called tournament algorithm, and the size of tournament is 4. So let's see the result of part 1. Okay, so we focus on the conventional jet programming and the random search-based pre-learning A and first. We can see that all of the measured data, the random search pre-learning A get better than the conventional generative programming. So it can prove that our work works. It can improve the performance for the generative programming. And let's say the random search-based pre-learning A and random search-based pre-learning B. So the difference between these two is the computation is different. For the A, we only have the 10,000 times computation. I mean, the computation means the 1 times evaluation of the fitness means 1 times computation. So the difference is for A, there has 10,000 times computation, and for B, there has 15,000 times. So the B got little bit better than the A. So that can prove that before the computation of the pre-learning achieved the threshold, the much computation means the better performance. So the second stage is, okay, for the second stage, we did a computation between the different random number generator. So at first, we just focus on the logistic mapping and the render. The second one, the fourth one, we can see that the logistic mapping gets better results than render. Also, you can see this average R square. The logistic gets bigger than the render. So we consider what causes situation happen. Therefore, for figuring out this problem, we picked another chaos mapping as to do the computation. So we picked the sign mapping and the turn mapping. So it is the shape of the distribution for some chaos mapping. We use the logistic mapping, sign mapping, and turn mapping. Let's focus on the shape of the distribution. You can see that the logistic mapping and the sign mapping is very similar, that more easily to get the result located between the 0.1 and 0.921. And sign is as well as logistic mapping, but for the turn map, it is quite different. It is more like a real random. It is very random, right? And for this figure is a bitmap for the use module. Okay, let's say the red button, this one, there has a module, it's called pseudo random. Because we think maybe it's not the feature of the chaos to make the logistic can get better results than the random. Maybe it's just because it's a special shape of the distribution cause this it can obtain better performance. Therefore, we build a pseudo-random module that looks very similar with the logistic mapping and sign mapping, but it is not a chaos mapping. It is just a random mapping. Okay, so let's return back to the results. We can see that for the logistic mapping and a pseudo-random and sign, these three module gets better results than turn and random. As I said, the distribution of the turn mapping is very similar with random. So from the result, you can see that the shape, the logistic lagged mapping can obtain the better results than the random lagged mapping. So maybe it can, so we thought it can prove our idea that actually it is not the chaos because the logistic can obtain the better result. It is just because it's spatial distribution, shape of distribution cause this problem, because it can obtain better performance. So let's see the part 3. Okay, so the part 3 we did comparison between the random search pre-learning and genetic algorithm-based pre-learning. Okay, let's focus on the last parameter. It is called total computation. That means we control all of the 3 algorithms with the same computation. And for the random search-based pre-learning and genetic algorithm-based pre-learning, we only sent 1,000 times computation for the pre-learning and 9,000 times computation for the formal genetic programming. So let's see how does the result looks like. Okay, so we can see from the chat figure that our method actually cannot get the more better result because the pre-learning is not fully discussed yet. We didn't assign enough pre-learning computation for the pre-learning yet. So that we can say that our proposed method may be not suited for those situations that the computation resource is very pressure. I mean, if we don't have enough computation resources, maybe our proposed method is not a good choice. Okay, so let's have a conclusion. So the first is a good probability mapping for each operator to improve the performance of the genetic programming. We can get this conclusion from the stage 1. Second is logistic mapping can obtain better results because it's specialized distribution. We obtain this result from the stage 2. And the third is proposed method is more suited for the case that has enough computation resources from the stage 3. And in the next future works. I mean, the first is solve the hyperparameter problem. We got some hyperparameter for the pre-learning so far, but the hyperparameter is not a good thing for optimization algorithm. I mean, for all of the algorithm is not good. We can only to set the hyperparameter by our experience. So we'd like to find a way to remove this hyperparameter. I mean, make it become a self-optimized parameter in our future study. And second is trying to combine the proposed pre-learning to the genetic programming process. So, we wasted so many competition for this pre-learning. So I think the better way is to combine this selection process to the formal genetic programming. Okay, so basically that is all my today's presentation. Thanks for watching. And if you have any question, you can leave your comments or send to my email. Thank you so much.